we shall start our next class. Something suspiciously blinks on this camera, but I hope it will not affect the quality of the record. So we continue into elements of mathematical logic, or we can call it algebra of statements. It will be too sublime, but it does reflect to some extent what we are going to do. Algebra of statements. First of all, what is a statement in mathematical sense? Statement. It's not exactly the same, it doesn't have exactly the same meaning and as statement in common sense. They speak sometimes about a politician. He made an important statement, and usually in mathematical sense it's not a statement at all. So statement, by statement we will mean a declarative sentence, which is not news for you. A declarative sentence that is true or false. So if I make a statement like this pencil writes black color, that's actually a declarative sentence saying this pencil is black, and it is a statement in mathematical sense. If some, again, politician or military leader says, with this pencil we will crush our enemies, in political sense it's a statement, of course, but from mathematical viewpoint it's not a statement, because we cannot determine whether it's true or false, and probably nobody can determine. We can make suggestions, but we don't know for sure. Statements can be depicted as points or subsets. In this sense, I should say right away that the algebra of statements, is a Boolean algebra. Boolean algebra. What is a Boolean algebra? The best example that everyone knows, or almost everyone, people usually know, is the algebra of sets, is a Boolean one. Algebra of sets is a Boolean algebra. We usually depict sets by some regions. For instance, this is set B, and this is inside it set A. And A is part of B, right? Or A is a subset of B. And similarly with statements. Suppose statement B this is a marker. This is a marker. And statement A this is a black marker. We can show schematically by the same diagram. This is a black marker. It's part of the statement, it's a marker, so B. Of course, if A is a marker, if A is a black marker, then it's a marker, yes? A implies B. A, this says, implies B, or B follows from A. So this is the example of following. Yes, a set is a subset of it. Yes, and another example, if for instance A says this is my car, and B says, suppose my car is Ford. This is a Ford-made car. So of course, if my car is Ford, A implies B. This is my car, yes? This denotes my car, and it is part of the set of the whole this family of Ford cars. What else do we have for sets? I will show you the complete analogy. Because the algebra or arithmetic of statements is exactly the same algebra as algebra of sets. Also, those of you who study in more detailed statistics and probabilities know that the algebra of probabilities is also a Boolean algebra. And it's not really a great discovery if we understand that probabilities can be illustrated by plane regions, right? Probabilities can be interpreted as areas of plane regions, and it shows very clearly all their properties. Probability actually is also one of these theory of probabilities is one of these areas of knowledge that can be completely axiomatized. Of course, we will need numbers here, but it can be presented in axiomatic approach proposed by a certain gentleman by name Kolmogorov. He was a Russian mathematician, very important one. He created a big school, and one of his achievements, one of his many achievements actually, he axiomatized theory of probability. So let's not deviate too far from our topic. What else do we have in the theory of sets? What operations we do on sets? We can have set A and set B. And we have the operation of addition or union, and for I will write here on top sets, and here I will write statements, and I will write all the analogies that we have for sets and for statements. So for sets we have, for instance, operation of union or addition, A or B. It says for statements, suppose A and B are statements, A or B or both, right? And this is operation of addition, or it's called also union. And this operation for statements we call a disjunction. addition or disjunction, both of them are taken with inclusion. What does it mean with inclusion? This or both means with inclusion. Or both belongs, so we include this part that belongs to both A and B. So I will say X is A. I will not rewrite it for sets, but I will rewrite for statements. Disjunction B. If X, you can say X belongs to A disjunction, or X is a X statement, because it's a statement. X is A. If X is A, or X is B, or X is both A and B. And how is it illustrated? It is illustrated, different color. It is illustrated by complete this area, A and B, and their intersection. This is their intersection. The whole this thing is a disjunction. Another major iteration, I can write it also here. Yes. Let's keep the same illustration for sets and for statements. This illustration is called intersection or product. A intersecting B. And it's called intersection or product. And for statements, it denotes like this, and it's called conjunction. For sets, it read A and B, so simultaneously A and B. For statements, it is A and B. So X belongs to A and X belongs to B. That's for sets. X is A and X is B. And of course it's been illustrated by this region. I can also paint it more like this region between two sets, yes? I can show this here. Examples. Examples are usually very simple here. Suppose A means a statement: the car under consideration is Ford. B means a statement: the car is red. So this first thing, A or B, A or B, include all these cars. Ford, and this one must be red. Yes. So A or B means the car is a Ford, or the car is red, or our inclusion, or a red Ford. What about the intersection? What about the intersection? The car must be Ford and must be red. A intersection with B, or A and B, the car is a red Ford. I think this part is pretty clear. What are other notations and symbols we are going to use? What are other notations we are going to use? Following and equivalence. Following and equivalence. A implies B. It says A implies B, or B follows from A. This can be illustrated by a Venn diagram. These circles, I don't know why it necessarily must be a circle, it can be just anything. Usually called in statistics and set theory Venn diagrams. So B is the whole this big thing, and A is inside it. So if something is A, it is necessarily B. It is a geographically easy to assign geographically. I live in Edmonton, therefore I live in Canada. And geographically it's pretty understandable. That's a city, it is inside Canada, I'm here, therefore I'm outside Canada. What else can be illustrated? There are some statements that follow from one another. A implies B, and B implies A. A and B are logically or somehow else mathematically equivalent. X squared equals to y squared in real numbers is equivalent to the statement absolute value of x equals the absolute value of y. And x squared equals to y squared is not equivalent to x is equal to y. Right? X is equal to y is more restrictive. If x is equal to y, then their squares are equal. However, negative 3 squared and 3 squared lead to the same number, and at the same time negative 3 is not equal to 3. What else we need to consider? It's all very, very easy. It's mostly common sense. That's why we believe this logic is inherent in us. Still we have to know how to use it. The negation. Negation of A. Denoted. There are many notations for this. Not A with bar on top, and that's the one I'm mostly using. It's a compact and convenient. Or some people write it like this. Not A. Or the most vulgar one, not A. Or maybe there are some others. There are many other notations. Just make sure if you studied this logic in some other subject, use different notation. I will probably understand it if you use it in your exam paper, but try to make it very clear. So what is this negation? Not A is false. It's a negation of A. Yes? It considers its statement in falsity of A. It's false if A is true, and it is true if A is false. So the negation of statement A, for instance A, this pencil is black. Not A cannot be a statement this pencil is red. Actually, in practical terms, by saying this pencil is red, we do deny the fact that pencil is black, but it does not cover all possible cases. This pencil is red denies pencil is black, and pencil is blue is also in the area of A negated, yes, and pencil is white or pencil is green and so on, yes. So the only negation is the pencil is not black. So it is pretty easy. Now, so these two things cover all possible cases. So I will say A, this junction with not A, is universally true. Really, one of them must hold, right? So people usually denote it somehow A and not A equals to I or U, and it means it's a whole, not A. It's a universally true statement. Yeah? It's pretty safe to say this pencil is black or it is not black. This statement is universally true. At the same time, these two, and this is called this principle of logic or law of logic is called the law of the excluded middle. The law of the excluded middle. So there is no third option, A or not A. Yes? That's why we could not say that the negation of this pencil is black, this pencil is red, because it would not include all possible cases. The pencil is black or it is red. No, it's not universal. It may be true in particular case, but not always. But if I say this pencil is black or it is not black, then it's always true, universally true. A disjunction with not A, these two statements cannot hold together, is universally false. This statement is universally false, or we can denote it like this. A disjunction with not A is, I think, use the same symbols people use for empty sets. I don't have a better notation, and it's called the law of contradiction. It's called the law of contradiction. So what happens as a result of these two laws? Do these laws follow from anything? How do we know they are true? Are there our statements that we prove, or they follow from our everyday experience or from our setting of the world? And they are, of course, principles of all axioms. They are called, these laws are called principles of logic, or you can say axioms. We accept them. Some philosophers do not accept them. These are usually sad people. But these laws, we feel it as part of our world. So we accept them, and what follows from them? If you take a universally true statement, I will show it like this. I do it intentionally ugly. Why? They always draw Venn diagrams with circles. I have no idea. And the whole world is divided. This is A, and this is not A. If you take the union of them, we get universally true statement. Intersection is empty, there is no intersection. So exactly one of A or not A must be true. Exactly one. These are important words. I will also underline them in red to show how important they are. If I just say one of them is true, it says nothing. Because one of them doesn't say about the other anything, yes? In everyday speech we do not say exactly one. Do you have a dog? Nobody will tell you, I have exactly one dog. Some people who want to be precise, yeah, I have dog. I have one dog. Do you have two dogs? Maybe you have more. You have one dog, but you may have the whole pack of dogs. You know? So, if you want to be precise, and you have really one dog, you can tell, I have exactly one dog. But we don't do it in everyday speech because people will think we are weird, yes? And we are slaves of societal conventions, yes? So we do not do too many exotic things. So this fact has a very important consequence. It serves as a basis. This is the basis of so-called proofs by contradiction. I don't have to have it in quotation marks because it sounds like more. No, they're really proofs by contradiction. So what is the essence of proofs by contradiction? They're actually part of our nature. We used proofs of contradiction in your lower level mathematical course in linear algebra, for instance. We use it all the time, and people did not ask to substantiate them any more than they are already sitting in our minds. So what is a proof by contradiction? Suppose we need to prove that A holds, A is true. We do the following. We suggest that A is not true, which is equivalent not A is true, and by logical steps, by drawing conclusions from this, from the statement not A is true, we arrive to a contradiction. Contradiction to what? Then I will write it in different way, because we arrive to a contradiction. Contradiction to what? Actually, in case of geometry or any other science, or even norms of behavior and so on, we can say the answer must be contradiction to axioms chosen. Eventually, axioms is our sacred cornerstone. We stand on our axioms. We believe they are true. So if something contradicts axioms, then it was wrong. If you get a fine for driving on red lights, then you can ask policeman, why do you fine me? Because your actions contradict our axiom, our traffic regulation. In traffic regulation we have an axiom. You stop at red light. You drive when it's green light. This choice had been done, and probably has some biological substantiation. Red is alarm, but altogether it was an axiom that we choose. Yes? And whatever contradicts the axioms is not true. Let's consider an example. Whenever possible, I will try to use geometrical examples. An example. Oh, another thing I have to mention. Proof by contradiction is denoted very often for brief. RAA. Altogether, I hate abbreviations, and especially people from administration, from higher administration, they speak these abbreviations. It's their new language, and nobody can understand it. And if you're not in so many committees, so you hear these words every day, you actually don't understand them. They could speak a foreign language that we don't know with the same success. Even in foreign language you can guess some words, but these abbreviations you cannot. So I don't like abbreviations. I don't ask you to prove. You can always safely write proof by contradiction, But RA is very easily deciphered and it has meaning. It's called reductio ad absurdum. And it's actually in Latin, yes? Reductio ad absurdum. So it is actually reduction to absurdity. So it has meaning and it is part of the slang of the subject, so it would be good if you can use it. If you don't, proofs by contradiction is good enough. But I think it's cool to know some Latin and Greek as well. Yeah? We will use very often Greek alphabet because this area of knowledge originated from Greece. Alpha, beta, gamma, delta, epsilon, zeta, and so on, so on, so on. So by the end of this class you will speak Latin and Greek, you will read Iliad in Greek without dictionary. I don't know if it will happen. It's a dream, it's part of it. It would be cool if we could, yeah? I know the Greek alphabet, but I cannot read it. I can read some words because I understand this. Letters, and also Greek was the basis both for Slavic languages and for Western languages, yeah? Because Latin originated in Greek and all the Western languages like English, French, German, they came from Latin, yes? Whereas Russian and other Slavic languages originated in Greek. That's our cultural intersection. And of course Euclidean geometry, the cultural intersection of all cultures. An example of a proof by contradiction. A circle has, what are we going to prove? About the centers of the circle. How many centers? 5, 6, 3, 11. A circle has not more than one. You can say a circle has exactly one center, but we already know it has one center. Does it have more? That's a question. So let's be very precise. A circle has not more than one center. By the definition of a circle, yes? By the definition, it's such a curve that every point of it contains all such points, so it is a locus, you remember? It is a locus of the points standing from a certain point called the center of the circle at certain distance. What is distance? Distance is a segment called the radius of the circle. So it doesn't say anything. It does say that the center must be, but it doesn't say how many centers are there. The proof. We will prove by reduction ad absurdum, by contradiction. What they want to say, that is not more than one center. Suppose some circle gamma, it's a Greek letter gamma, mathematicians and even physicists like denoting curves gamma and circles in particular. It's a capital gamma. Small gamma, lowercase gamma looks like this. I will write it separately, like this. Suppose some circle gamma has more than one circle, more than one center. more than one center. O1 and O2 and maybe others, I don't know. So I will draw this circle, of course we're in geometry, so we will draw things. O1 is a center and O2 is also a center. You can see clearly that neither of them is a center, yes, or one of them is not a center, but imagine this circle, 20 kilometers, radius 20 kilometers, and I will make these two centers at the distance 5 centimeters between each other and close to the center of the, you will never say which is in the center, this is not. Now, O1 and O2 both centers. By axiom 1, I can draw a line through these 2 points. I can draw a line, and it will intersect the circle at some points A and B. Draw a line O1, O2. We can do it by axiom 1. We always substantiate. Can we do it? Always ask yourself, can we really do it? Can we do it? Yes, we can. By axiom 1, you can draw lines through the points. It will cut gamma at A, B. Right? Then, by definition of the circle, AO1 equals O1B, because they are radii connecting points of the circle with the same center, O1. Similarly, AO2 is equal to O2B. Yes, these two guys, they must be congruent because they are radii of the same circle.